You see on the board 3 equations from Physics 20 that you should recognize. The first one, at the top of the page, Fg is equal to gm1m2 over r squared, finds for us the force of gravity that acts between two masses a certain distance r apart. It will be used every single time to find a force of gravity. Now there is an equation that's analogous with electricity. That's Coulomb's law. F is equal to k q1 q2 over r squared. It also enables us to find force, but this time it's the electric force that acts between two charges a certain distance r apart. We've used this equation several times. We'll continue to use it throughout this unit. The second equation that you see on the left-hand side of the page, little g is equal to big G m over r squared, finds for us gravitational field strength that is caused by a producer. The Earth acts as a producer to objects that are on or near the surface of the Earth. If you are sitting on the surface of the Earth, you are an experiencer. The Earth is the producer. If we have more information about the Earth than we do about you, then we would find the field strength using the second equation. We'll call it the producer equation here. Now, there is an equation with electricity that's analogous to this, of course. We're going to say E, the electric field, caused by a producer, caused by something that produces a field, is equal not to Gm over r squared, but rather kq over r squared. This q, by the way, is, of course, the charge of the producer, the charge of whatever it is that's causing the electric field. R is the distance from the center of the producer to wherever it is that you're trying to find the field strength. Finally, the last equation, G is equal to Fg over m. This is the gravitational field experiencer equation. Once again, if we talk about the Earth being the producer and you are sitting on the surface of the Earth as the experiencer, this time if we have more information about you, the experiencer, we would use this equation. We'll call that the experiencer equation. And of course, there is an analogous equation for electricity. We're going to say electric field experienced by something is equal to the electric force experienced divided by the charge of the experiencer. Pay close attention here. This is the charge of the producer. This is charge as well, but a completely different charge, the charge of the experiencer, whatever it is that's feeling the electric field. I've got some examples to give you here today, starting with example number 1. It's on the sheet that I gave you on the first day of this unit. It says, determine the electric field strength and direction 50 centimeters to the right of a sphere that has a negative charge of 25 microcoulombs. We're going to circle this. We're going to circle this because we're non-standard units. We're going to write down a little bit of givens here. We're going to say r, the distance from the charge, is 50 centimeters or 0.500 meters. The charge here is 25.0 microcoulombs. This would be the charge of the producer. We're trying to find the field strength a certain distance away from this charge. Trying to find the field strength right here. This point right here can't possibly be experiencing the field. Okay, this is the producer that's causing the field right there. Now, we know the direction already. It's to the left because the direction of the electric field must point toward a negative producer. We know the field points to the left, but what's the value of that field? Well, we're going to use the producer equation. We're going to say E is equal to kq over r squared. That's 8.99 times 10 to the 9 times the charge of the producer, which is 25 times 10 to the minus 6. What is it that's experiencing the electric field out here? I don't know. Right now, we don't have any information about what experiences that field. We only have information about what produces that field. The distance is 0.500 meters. Don't forget to square that. We do the math here. It works out to be 8.99 times 10 to the 5 newtons per coulomb. mathematically, and we know it's to the left because once again up here, it told us that it's a negative producer. To the right of a negative producer, the field must point to the left because it's acting toward that producer. I'd like you to take a few minutes right now and work on worksheet number 8, questions 1 to 4. Example number 2. This one says 100 nanocoulomb charge experiences a force of 4.00 newtons to the left. Determine the magnitude and direction of the electric field at that point where the 100 nanocoulomb charge experiences this force. We're talking about an experiencer. We know we're going to use that experiencer equation. Let's write down some givens here. The charge of the experiencer, I don't know what causes this field. Something does, but we don't know what it is. We know that charge is of the experiencer is 100 nanocoulombs, or 100 times 10 to the minus 9 coulombs. We know the force experienced is equal to 4.00 times 10 to the negative 5 newtons. And we know it's to the left. We know the force is to the left here. We wanted to find the magnitude and direction of the electric field, where the charge experiences this force. We're going to say E is equal to F over Q. This is the way the equation appears on your data sheet. My suggestion to you is to add some absolute value signs. Don't try to find the direction from the equation. It's going to lead to trouble. Just find magnitude. The magnitude of this force is 4.00 times 10 to the negative 5 newtons. The charge magnitude is 100 times 10 to the minus 9 coulombs. This gives us an electric field strength of 400 newtons per coulomb. There's the magnitude. Now, what about the direction? We know the force points to the left. It is a positive charge. I'm positive the force is with the field. If it's a positive particle and the force is to the left, then the field must also be to the left. So we're going to say the electric field is 400 newtons per coulomb to the left. Now I'd like you to take a look at worksheet number 8, questions 5 to 7, please. Example number 3 says determine the magnitude and the direction of the electric field midway or halfway between a 100 microcoulomb charge and a negative 75 microcoulomb charge that are 20 centimeters apart. We should draw a diagram for this one. We have a positive charge that is 100 microcoulombs. We have another charge over here that's negative that is 75 microcoulombs. We know that our distance between the two charges is 0.200 meters. And we want to find the field strength right here, midway between those two charges. Now, we're going to call this one number 1. We're going to call this one number 2. The field at this point midway between caused by number 1 is to the right. It's to the right because the field points away from positive producers. Now, the field caused by number 2 is also to the right because the field points toward negative producer. So E1 points to the right away from this guy. E2 points to the right toward this guy. In the end, the net effect is that they both end up pointing to the right. Now, let's find the value of each of these fields. Let's say E1 is equal to KQ over R squared. These are both producers, by the way. These are both producing a field midway between the two of them. E is equal to KQ over R squared. Let's say 8.99 times 10 to the 9 times the charge of the first producer is 100 times 10 to the negative 6 coulombs, divided by the distance from the producer to wherever it is that you're trying to find the field strength, that is midway between the two charges. We're going to say the distance is 0.100 meters because it's halfway to the other charge. That gives us a field strength of 8.99 times 10 to the 7 newtons per coulomb. Now, E2 is equal to KQ over R squared as well. It's the constant times the second charge, 75 times 10 to the minus 6 coulombs. We're dropping the sign of a charge because we always do when we're subbing a charge into an equation. The distance, once again, is 0.100 meters because that's how far that x, that point is that's midway between the two charges, is from the second charge. Let's solve for this one. We end up getting 674.25000 newtons per coulomb. Now, we combine them. The net electric field is equal to E1 plus E2. Now, as it turns out, these are both positive, as we have them both drawn to the right. But you can imagine how next time around, you might have one of those fields that's drawn to the left. And if that's the case, we'd simply make it a negative value when we sub it into this equation. When we add these up, we end up getting a value of 1.57 times 10 to the 8 newtons per coulomb. And we know the direction of that is to the right. I know that, of course, because it's a positive value. A negative value would have meant that it was to the left. Now I'd like you to take a look at worksheet number 8, questions 8 and 9, please. One more equation that we need to introduce now before we give you the next example. But before I give you that equation, I'm going to review the other two equations that we've already done. The first one is the experiencer equation. We know that the electric field between parallel plates is uniform. That means that it ends up being the same strength no matter where you look. This is a non-uniform field that surrounds a producer. So is this. We know it's a non-uniform field because the field lines are not parallel. Here's two parallel plates, two metal plates like bumper cars, right? The roof of a bumper car and the floor of a bumper car that are both charged. One plate is positive, one plate is negative. The field that acts between those two plates, from the positive plate to the negative plate, because field always points away from positive toward the negative, is a uniform field. We know that it's uniform. We look at this diagram, the field lines are parallel to each other. Here, it's non-uniform because the field lines are not parallel. Here, it's uniform because the field lines are parallel to each other. The experiencer equation can be used with a uniform electric field. It can also be used for a non-uniform electric field, but right now we're learning this whole parallel plate thing, so we're going to say that it's valid for a uniform electric field. Now, the producer equation that we already learned as well, E is equal to KQ over R squared, is not valid in this new situation of uniform electric fields, these parallel plates. It's only valid in a non-uniform field. So this one is good here and here. This one is only good here in the non-uniform electric field. It's not good for this one over here. We can't use it for a uniform electric field, which is parallel plates that are charged, because those field lines are parallel to each other. And this equation mathematically gives me a different value for the electric field, but depending upon position. In this situation, where we have a uniform electric field, the electric field is the same no matter what the position is. So the first equation, E is equal to F over Q, we're allowed to use whenever we want. The second equation, the producer equation, we're allowed to use in a non-uniform field. Well, now we need a producer equation that's valid for a uniform field. And that's this new one. This new one that we're learning right now. This is a producer equation as well, but it's a producer equation for a uniform electric field when we have two charged parallel metal plates. E is the electric field. Delta V is what we call the potential difference. The potential difference between the two plates. We talked a little bit about that earlier on. We said potential difference is similar to height. Potential difference in itself provides a charge with energy. In itself, it's not harmful. In itself, it's no more dangerous than height is in a building. It's only when the potential difference causes electrons to move that it becomes an issue, just like when the height of a building causes you to move off the edge, that it becomes a problem. Potential difference is measured in joules per coulomb. This is the amount of joules that we have per coulomb of charge, which is exactly the same thing as a volt. So we can say potential difference is 10 joules per coulomb, or we can say it's 10 volts. Delta D is the distance between the plates. And that's, of course, going to be measured in meters. The potential difference between one plate and the other divided by the distance between the plates. This infers that no matter where a charge is between these two plates, the electric field strength will be exactly the same because the potential difference between plate 1 and plate 2 will be the same, as will be the distance between the plates. This delta D is not where this charge is or where this charge is. It's the distance between the plates, and of course delta V is the potential difference between those plates. Now, what are the units for this electric field? Well, we can still use newtons per coulomb, just like we did with the other equations, but we could also now say a newton per coulomb is equal to a volt per meter. Now, I've got one more example to give you here. This is example number 4 that appears on your example question sheet. It says a potential difference of 20 volts exists between two charged parallel metal plates that are 3 centimeters apart. Top plate is negative, bottom plate is positive. What's the magnitude and direction of the electric field between the plates? Let's draw this out. Top plate, it says, is negative, and the bottom plate is positive. That gives us an electric field that points upward. Remember that the electric field points away from positive and toward negative. So we've nailed the direction already. The magnitude of the field. Remember, this is a uniform electric field. We're going to use the uniform electric field producer equation down here to find the strength of that field. This one's not valid. This one is if we experience a field, but we're going to use this one because it's producing the field. We're going to say E is equal to delta V over delta D. The potential difference here is 20.0 volts. The distance between the plates is 0.030 meters. That gives us a field strength of 666.6667 volts per meter, or we could say 667 volts per meter. We could have also said 667 newtons per coulomb, but volts per meter works just as well. So we've got the magnitude, 667, and the direction is upward, away from the positive plate toward the negative plate. B says, what's the electric force experienced by a proton if it was between the plates? Well, if you remember, this first equation, E is equal to F over Q, that has force in it, is valid in a uniform or a non-uniform field. We've got a uniform field now, but we're allowed to use that equation that we used yesterday, E is equal to F over Q. So let's do it. Well, let's rearrange it, solve for F. The charge of the proton is 1.60 times 10 to the minus 19 coulombs. The electric field we just found to be 666.667. Solve for that. We end up getting 1.07 times 10 to the negative 16 newtons. And finally, question C says, what's the acceleration of the proton from B? How do you find acceleration in physics 30? The force needs to be with you. Well, it is with us. We just found it. And then once the force is with you, we're going to say A is equal to F over M. The force is 1.06667 times 10 to the negative 16 newtons, divided by the mass of the proton, which is 1.67 times 10 to the negative 27 kilograms, gives us an acceleration of 6.39 times 10 to the 10. Say newtons per kilogram there, but we could also say 6.39 times 10 to the 10 meters per second squared. Finally, to finish off your day, I want you to complete worksheet number 8, questions 10 to 12.